Alright, into the second part of this video, and we want to go ahead and talk about models and how we can use these models to understand a little bit more about the world that we interact with on a regular basis. Now, as stated on the screen, models are our attempts to understand or to explain something that's happening at a level that we can't even understand. Things that are at the microscopic level, whereas we are based on experience in the macroscopic world. Now, when we look at atoms, this is one of the big things that we'll have to use. We have to use models because, of course, they're too small for us to actually interact with. Now, things that you have to keep in mind. A model does not necessarily equal reality. So I can predict or come up with a model to explain why high school students arrange their schedule in a certain way. Now, I could have implications of that, and there could be very true um, observations that go along with it. But the model does not necessarily have to be um, the reality of how things actually work. Now, most times they're actually oversimplifications, trying to take something that's very complex and to make it simple enough for us to understand. Now, as we continue to understand more of them, we realize and we add more to it. That's why we say it becomes more complicated, because we then take away a lot of those underlying assumptions that we usually hang our hats on and say, well, this is why it happens, or this is wrong. Now, one of the beautiful things about using models, though, in the long run, is it helps us to be able to understand where we went wrong and why we went wrong, and understand a lot better what's happening within the atom or within the system it is that we're actually observing. Now, we use different models to help us also to understand how it's going to work in terms of our energy change, because as we talked about with thermo, we looked at the overall change in energy or change in enthalpy for a reaction. But another thing that we can do is we can actually look at the bond energies. What bonds are broken and what bonds are formed. And that's going to help us to understand the overall chemical reaction. Now, to break bonds, we have to add energy to the system. Therefore, this is going to be an endothermic process. You guys thought we were done with that, but nope, we got to bring it back. Now, to form bonds, we're actually going to release energy. When they form, remember we said that they'll be lower in energy, so that energy is going to be released out into the surroundings. This means it's going to be negative charge or exothermic. And we're going to find that it's actually our delta H, our change in energy, is going to be equal to the integer, meaning however many of those bonds are being broken, times the energy per mole of those bonds. Now, this part is always going to have a positive sign. The D part is always going to have a positive sign. Minus the energy of the bonds that are formed. Again, integer times, or the number of those, times the amount of energy per mole of that bond. This is going to help us to get a bigger picture of what's going on. So, in this case, it asks us to predict the delta H for the following reaction. We have to look at the model that we have here. We have CH3N with a triple bond on our carbon here, and it's turning into this compound. What bonds are broken, what bonds are formed, and that's going to give us an overall picture. Well, let's take a look. I'm going to break 3 of my carbon-hydrogen bonds here. So 3 times 413. I have to break each of those. And, sorry, taking a look, I'm breaking a bond also, a carbon-nitrogen bond. So just breaking one of those. So plus 305. And we're rearranging to get this bond taken care of, 891, and we only have one of those. Now this is going to be minus, sorry, we have bonds formed. This is still going to be 3 of our 413 plus 1 of our carbon-carbon bonds, because we didn't have that before. which is 347, plus, again, we reform this bond, our 891. Oops, I said 891. 891, there we go. Now, in finding this out, or figuring this out, we should come out with a delta H value of approximately negative 42 kilojoules. We're going to note that a lot of the information was basically the same. The only main difference that we had here was the addition of our carbon, sorry, our carbon-carbon bond that we hadn't accounted for before. And that's going to account for our negative 42. Oops, and I realized I actually have, no, it's set up correctly. It's set up correctly. Now, in trying to understand how these atoms and these molecules, sorry, are going to work together, we're actually going to develop or use a model called the localized electron model. This is the foundation that we use when we attack our Lewis structures that we were drawing before. And I know we're some are really not big fans of Lewis structures, but we're going to run through very quickly how to do those, just to give you a little reminder, a little refresher. But in the localized electron model, a molecule is composed of atoms that are bound together by sharing pairs of electrons, which we talked about before, using atomic orbitals of the bound atoms. Electron pairs are assumed to be localized to a particular atom between the space of two atoms. Lone pairs, these are the ones that are not shared, and bonding pairs, these are the ones that are actually involved in the bonding process. Now, description of this arrangement is what we usually call the Lewis structure. The prediction of the geometry or the shape based on that is what we call the VSEPR model, and we'll talk about that in just a second. Now, description of the atomic orbital types used of the atoms also help us to understand how the lone pairs are arranged. Starting off with Lewis structure, they show us how the valence electrons might be arranged around the molecule. And it's going to reflect the central idea that stability of the compound relates to noble gas configuration, or them following the octet rule. So, if we look at what we have here, I have two hydrogens. Each one has a single electron. When they come together, they share those electrons. And so we demonstrate that by having the overlapping barriers, showing that those are actually shared between the two. Now, that works for hydrogen because hydrogen only needs 2 electrons. What about when you need 8? So, when we look at something like fluorine, fluorine has 7 valence electrons. So, with those 7 valence electrons, it's just in need of 1 in order to fulfill its octet rule. So, what we're actually going to find is that just like we saw before, if I can extend this down, there's actually 2 electrons that are going to be shared between each of these. And those 2 electrons are going to complete the octet rule for each of our fluorine atoms. Single covalent bonds, we share 1 pair. Double, we share 2 pairs. And triple, between 2 atoms, we share 3 pairs of electrons. Now, when writing Lewis structures, 1, we have to make sure that all of our valence electrons are taken care of. 2, we use a pair of electrons to form a bond between them. And most times we'll draw them as a dash when we do ours. 3, atoms usually have noble gas configurations. So we want to always try to set it up so that we reach the octet rule or duet rule for hydrogen. So in the case of what we have here, we have a total of 8 valence electrons for water. So when we bond them together, we're going to set it up so that we have a pair being shared between each. So that's 2, 4, and we have to make sure that we also include the lone pairs, which is what we have here. This is why we have these 2 pair of electrons that are there. They're the lone pairs, or the non-bonding pairs, that help satisfy the octet rule for our oxygen. The same thing is going to happen when we deal with phosphorus, okay? For PBr3, sorry. Similar for HCN. Now, there are going to be some exceptions to this rule as well. When we look at things like boron, boron only has 3 valence electrons. So it can't exactly make it to 8 valence electrons. It can't have a complete octet, but we can fill that outer layer as much as possible. And so with BH3, we end up with 6 valence electrons, 3 single bonds that are formed around it. We're also going to have some that we can find that go above and beyond. These are going to be the elements that are usually group 3 and below because they can access the d orbitals that are provided to them. Because of this fact, this is going to allow them the opportunity to actually have some valence electrons extra that are hanging out there. So they're going to go beyond the octet, as sulfur here ends up having 10 valence electrons. Similar thing for arsenic here. Now, just as a quick review, carbon, nitrogen, oxygen, and fluorine always assume going to follow the octet rule. Boron and beryllium have too few, so they're going to end up with less than 8. The second row never exceeds, and the third row, heavy elements, can usually satisfy the octet rule, and they can even go a little bit beyond that. Now, we're going to skip over the resonance part just a little bit, but I want to give you an idea that the Lewis structure is also going to help to play a role in how the electrons are going to be arranged. So we're going to start off with what we call VSEPR theory, or VSEPR model. Now, the VSEPR model, or VSEPR model, stands for the valence shell electron pair repulsion. Basically, the idea is that the atoms are going to arrange themselves in such a way that they will create the least resistance between each other. So the electrons are going to try to get as far away from each other as they possibly can. Now, when we're applying the VSEPR model, a couple things that we have to do. First thing is we have to draw the Lewis structure. Second, we have to count the electron pairs and arrange them in a way that minimizes repulsion, or we have to try to put them as far away as we can. Then determine the position of the atoms from the way the electrons are shared, and then determine the name of the molecular structure from the position of the atoms. Have a little short video clip here.
Minimizing electron pair repulsions. 2 bonding electron pairs around the central atom result in a linear structure. Carbon dioxide has a linear structure. The bond angle for a linear arrangement is 180 degrees. 3 bonding electron pairs around the central atom result in a trigonal planar structure. Boron trifluoride has a trigonal planar structure. 4.
Now, as you notice, I was probably skipping through, and don't worry, I'm going to come back to those in class. But to get the idea, depending on how many things are bonded to it and how many electron pairs, lone pairs, are still left, that's going to help us to determine the shape and also the bond angles. Okay? Now, this is also going to carry us into a little bit of what Chapter 9 talks about, which is our hybridization and our molecular geometry. It's going to look even deeper at those different shapes and help us to understand how that's all going to play out. We want to move past this part just a little quick, and they're good questions. Now, when we look at the amount of, or the number, sorry, of electron pairs, this is going to give us an idea of how it's going to work in terms of the VSEPR shape. Now, as was mentioned in the little video clip, if we have 2 pairs of electrons, as we see here, we're going to end up with a linear shape. 2 pairs being shared, we have linear. 3 pairs being shared around the same atom, you notice that we have what's called trigonal planar. Now, this is not including if we have how many things we actually have attached. That's going to come in with the molecular geometry part. But just looking at how many spaces that we have where the electron pairs can be shared, this is going to give us one piece of the shape. So with 4 electron pairs, we have tetrahedral. 5, we have trigonal bipyramidal. And 6, we have what's called octahedral. Each of these showing where we have the ability to form or to share electrons, okay? Not necessarily saying that they actually are shared at those points, but we have the ability to do so at those points. Similar thing is going to happen as we continue to look a little bit further over it. Oops, sorry. Now, within this tetrahedral shape, notice that we can have a couple of things that are going to happen. First, where all four things are connected, we call that shape tetrahedral. We also can have where only three things are connected, but there's also this lone pair that's hanging out there. Or maybe even it's all gone. This we would call a trigonal pyramid. Or in the case of what we have for water, if I use this and put the lone pairs there, it makes it a little clearer, we get what's called a bent configuration. All of these have four regions around them where we can actually form bonds. But based on how many things are attached, that will give it the actual name of the shape. Similar thing happening here. Trigonal bipyramidal when we have all five attached, but if we no longer have this one attached here and we just have this open space of electron density, then it becomes what we call a seesaw, which makes sense. These are the legs and these are the parts of the seesaw. If we have these two are gone, but we have this piece here, three things are attached, we have T-shaped, and if each of those regions are actually gone, we end up with something that's linear. Five pairs around it or places around it where we can actually bond and form something, but depending on how many things are there will determine what our actual shape is. Now, we're going to pick this up in class tomorrow and we're going to see if we can't find ways to make this part stick a little bit. I know it's sort of weird and that part is sort of just memorization, but we're going to try to work our way through it as best as we can. Have a good evening and see you in class.